Good morning, student. Now I'm going to discuss with you, explain to you what is Lindelof covering theorem. So in the last explanation, I have shown you the proof of the lemma, which is an important part of the Lindelof covering theorem. With the help of that lemma, we are going to prove this theorem. So what is this Lindelof covering theorem? It states here, A here, assume A is a subset of Rn, and F here an open covering of A. By open covering of A means F here is a collection of this form. F here is collection of set of this form O alpha, such that alpha belong to indexing set where each O alpha is open. Okay. So F is an open covering of A means that the union of O alpha belong to indexing set I covers A, or we can say that A is contained in the union of O alpha, since F here is an open covering of A. Then what we need to show that among this collection covering of F, there exists a countable sub collection of this O alpha, means among this also there exists a sub collection of this O alpha which still covers A. So how we prove it? So we start here with this lemma. So you take G here, let G is equal to collection of all n balls having rational n balls. This is n balls collection. Okay, collection of n balls having rational center and rational radii. Okay, having rational centers and rational radii. So this A1 can be of the form A y bar cubed, where y bar is a rational numbers, where each entry of this y bar is a rational numbers, and cubed here the radius is also a rational number. So A1, A2 will be of this form, where the center is a rational numbers and radius is also rational. So the collection, so G is the collection of such all n balls. With this set G, with the help of this set G, we are going to prove that there exists a countable subcollection of this which still covers A. So here what we have, which covers A. So assume here X bar belong to A. Okay, X bar belong to A, and since F is an open covering of F, but A is contained in union of O alpha, means A is covered inside this, alpha belong to indexing set. It implies that there exists this O alpha which belong to this collection F. Okay, the collection F, what is this collection F? O alpha belong to indexing set such that X bar belong to O alpha. But by this lemma, let G, if G is collection of all n balls having rational centers and rational radii, and X bar belong to Rn, and let X be any point, be any open set, compare this S with this O alpha here. Okay, this S, compare it with O alpha, then there which contain X. So as you can see, O alpha contain X bar, so therefore there exists at least one n ball by this lemma. Then there exists at least one n ball in G, that is this collection of all n balls having rational centers and rational radii, such that this n ball is contain X and is contained in S. So here by that lemma, using this lemma, we have shown here X bar belong to O alpha, as we have shown here, as X bar belong to O alpha, it implies that there exists at least one n ball in set G. What is set G? G is a collection of all n balls having rational center and rational radii, such that is there exists at least one n ball in G, say AK. Okay, such that X bar is contained in AK and is contained in O alpha. With the help of this lemma here, you just simply replace this S by O alpha here. Then for X bar belong to A, there exists set O alpha belong to this collection F, which which contain x bar, and by this lemma, if since O alpha is open, so there exists this O alpha is open because F is collection of open covers of A. So there exists an n ball which we extract from this G here, this collection of all n balls having rational centers and rational radii, such that this x bar belong to AK and is contained in O alpha. But there will be infinitely many AK. Okay, there are infinitely many AK, that is how many n balls, say AK, having rational centers and rational radii which contain x bar. So that is, it can be A1, A2, A3, A4 and so on. But we are going to take the one with the smallest index. So for example, if you have A1, A2, A3, they are all n balls which contain x bar. So I'm going to take the one with the smallest index, that is 1, 2, 3. The minimum of this 1, 2, 3 is 1. So I'm going to take, say, A1. So in general, I'm going to take this X as AM, AK as AM. Infinitely many AK, but we choose with the one with the minimum index or the smallest index. Okay, say M is equal to MX. M here is a positive integer, which an AK here, such that then we can have here, then we have X bar belong to AMX, which is same as AM, okay, is contained in O alpha. So we are going to choose only the one with the smallest index, say M is equal to AM or MX. That is, you have X bar belong to AMX is equal, which is equal to AM is contained in O alpha. Then now what is X bar? X bar is an arbitrary element of A. So as x bar varies, so for different elements x bar, there are x bar varies for x bar, it is as x bar varies over an elements of the set A. So therefore the collection of the set of all n balls having rational centers and rational radii, the set of all n balls obtained here as x varies over all elements of A is a countable collection of open sets which covers A. So here, because there are infinitely many AKs, so we choose one with the smallest index AM, such that x bar belong to AM is contained in O alpha. But as so the collection of all those AMs with smallest index as x varies over all elements of A will form a countable collections of open set which covers A. Now to get a countable subcollection of this open covers of F, we simply, so to get a countable subcollection of F which covers A, we simply correlate to each set, to each set AMX one of the set O alpha of this collection F containing AMX. So to obtain the countable subcollection of F which covers A, we simply correlate this to each set AMX of the set O alpha, because F O alpha belong to this countable collection of open set which covers A. So we simply correlate this to each AMX, that is this collection of all those n balls having rational centers and rational radii which covers A. We simply correlate to each of those collection of sets to one of the set O alpha which belong to F, which contains AMX, and from there we will obtain their countable. So therefore, if F here is this O alpha belong to indexing set I, where each O alpha is open. So therefore we simply correlate, means this one, or we simply replace this O alpha by this one, by AMX. To each AMX we correlate this each AMX to one of the set O alpha in F which contain AMX. So therefore those collection which lies inside this O alpha will form a countable collections of this sets A. That is, A is contained in union of AMX. MX belong to indexing set I, and this is contained in union, O alpha. Okay, alpha belong to indexing set I. Say lambda, where lambda here is a subset of I, we can say. So I hope it is clear to you what is this Lindelof covering theorem. That is, assume a subset of Rn and there exists an F be an open covering of A, then there is a countable subcollection of F which covers A. So I hope it is clear to you. So the next proof, in the next video, I'm going to prove you as Heine-Borel